So this is, I guess, our penultimate class, our last lecture. Next Thursday, you will do your presentations. I will not be here almost all of next week until Thursday morning. So if you have questions, send me email. If you really need to talk, we can set up a Skype session or something like that. I'm going to be in Chicago, so it's slightly different time zone, but more or less equivalent. But it will not be in my office hours, and I will send an announcement so that you'll know. As I said last week, please fill out your student perception of instructions. I take them seriously. As I won't give you the speech again. I will, remind you that when you log in, I think, those banner notifications that everyone ignores and then closes. One of them says fill out your SPIs. I think we're in the middle of it now, right? We've like a little bit less than a week to fill them out. If you haven't yet, do it, please. And in case you forget, you can go back. I put my course objectives. You can go and read the course objectives. You can say, were they achieved? Did he do that? Can I do these things now? Okay, so we all know I'm extremely funny. Unfortunately, that is not one of the measures that they ask. No one's laughing. Okay, maybe I'm not that funny. Okay. So today, what I would like to focus on is scientific data visualization. And I'm stealing slides, and mostly I'm going to poke at one or two pieces of software so you can get a sense for it. So there's two kinds of scientific data visualization or scientific visualization software. One is our proprietary to the specific piece of software that's being run. So for example, a lot of people over materials run a piece of software like star CCM, which is for finite element, finite volume modeling, usually for computational fluid dynamics. Star CCM has a visualization tool called Star Viewer, which you can use to do whatever visualization you're going to do of, say, fluids or what have you. And the other are generic or general tools. So there's two sort of high-level general tools that are well used in the scientific visualization world. One is ParaView. We're going to talk about ParaView today. And the other one's called Widget, which I'm not going to talk about. So we're going to talk about two tools today. One is an example of one is an example of the other. I guess I should have done the intro the other way around, because I'm going to first talk about the general tool, ParaView, which is freely available. Anyone can download it. It reads many, many different file formats, as we'll see, for lots and lots of different kinds of tools. As you'll see as we move along, ParaView is in some ways really crufty. It's not bright and shiny and so forth like, say, Tableau was for data visualization. However, it's an immensely powerful tool. There's a lot of great advantages to it. And the second one we're going to look at very briefly is called VMD. That's for doing visualization of molecular dynamics. And that's an example of a piece of software that is written specifically for the task of molecular dynamics. That's what it does. I know most of us here don't do molecular dynamics, or maybe you don't do fluid dynamics, etc. But it's good to know what these tools are and how they're available, because they could be relevant. I had a student in this class a year or two ago who was over physics, and she did astronomy, and she was trying to plot all these particles in R, actually, and because of overplot and the sheer number of things, it was a real challenge just to render it. Moreover, and that's one of the things these tools do well, is that they really have high-performance computing in mind, because mostly the people who are using a tool like ParaView are using high-performance computing in order to run the underlying simulation itself. So they're comfortable in the HPC world. In fact, the people who wrote ParaView are themselves quite familiar with that world on many different levels. I don't know, you guys are in computer vision. Did you know Sadat Dozier? Yeah, Sadat was involved in one of the original iterations of ParaView. So anyway, so it's good to know what you have available to you. So we'll talk a little bit about ParaView. I'm going to follow a script because I'm not at all an expert in ParaView. I'm going to skip around a little bit because we're not going to do everything that's in here, and we're going to just touch on a tiny percentage of what it can do. And then we'll talk a little bit about BMD. After that, my PhD student, Audrey Brune, who's in the back here, is going to show you how she's using ParaView and what she's doing right now with her dissertation. Then we'll do a little show and tell, and I'll walk around and I'll show you the visual, and we'll go into the 220 to see things in 3 dimensions. And those of you who are following along at home, sorry, you're not going to see the visual or the 3D thing, so you'll just have to imagine what it's like. Okay, so just a basic introduction here. So ParaView is open source, it's freely available, it's scalable, it runs on every major platform, albeit, in my experience, I don't think the people who developed it run very frequently on a Mac, because that's some weird bugs. I don't know, does it have some weird bugs in Windows?
A few, yeah.
Okay, so it just has some weird bugs, I guess. All right. But the cool thing is it has support for distributed computation, and we'll get to that toward the end. But you can run pieces of the so it's fine. We know that if I'm doing some massive simulation at really high scale resolution, I might need to run across many computers and many cores and use sophisticated computational techniques and yada yada yada. We normally don't think about that from a visualization point of view. But what if you have a mesh that's got literally millions of vertices in it, and you have to visualize these, and not only are there millions of vertices, but you have a time step every 10th of a second or 100th of a second, and you want to visualize it as quickly in real time as you can, right? It turns out for some of these tasks, just the visualization is computationally intensive. And so tools like Widget and ParaView will actually allow you to run servers that farm out the rendering tasks and other types of tasks that are available. The slides I get from Kitware, the company that makes it, claim that the interface is intuitive. Okay, my intuition is maybe not their intuition, but if you're used to 3D software, there's some stuff that you will find recognizable. It is very extensible, has lots of plugins. It already natively supports reading of many, many, many kinds of files, including star CCM and OpenFOAM and these sorts of things. We'll talk a little bit about that. But it also allows you to build plugins to read other things, which is very nice. And it does have a commercial maintenance and support contract. Moreover, if you're a part of if you're part of a Exceed allocation, that's the national program that gives people computational resources at universities. They have a whole program dedicated to assigning people resources to help them construct scientific data visualization, and by and large, they use ParaView. It's also very scriptable using Python. I'm not going to talk about scripting today, but it's in the slides. You can. So we can get a sense for at least what some of these things look like. A lot of them are fluid modeling or streamline modeling and these sorts of things. Yeah. Yeah, we don't care. All right. So it's none of the examples I'm going to show you today really capture its power per se, but it's used for visualizing very, very, very large structures. And it has an architecture that's quite robust. This VTK layer is for the reading of VTK formatted data structures. That's the Visit toolkit. So it leverages Visit, although I think ParaView is better than Visit. And then under the hood, it does a lot of different things, including OpenGL. It handles MPI if you're doing distributed computation. There's even a variant of it, and I think now they're trying to fold it into the main trunk where you can produce ray traced images. I'm not going to talk about ray traced images with ParaView, but when we get to VMD, I will talk about ray tracing and why that's, for scientific visualization, that's often what you want to do. So, for the final product. But it can be run in this client server mode. It can be run with a Python front end, so you can script things in a lot of different ways. Yeah, we don't care. Yeah, we don't care. Yeah. Okay. So predominantly, ParaView is really built around the idea that you're visualizing something that exists on some kind of mesh. It could be a regular mesh, an irregular mesh, what have you. Typically, if you're familiar, how many people in here are familiar with, let me reverse that. How many people in here are not familiar with the notions like finite element or finite volume or finite difference modeling? Right, so differential equations, people know about differential equations. So when you're doing differential equations, there are lots and lots of different ways to solve them. One way to solve them are using these types of methods. A subset of those methods involve breaking down a space, usually a physical space, using some kind of mesh, discretizing a space in that way, and then you're typically solving systems of equations across the links in that mesh, usually partial differential equations in the case of sophisticated models like computational fluid dynamics, because computational fluid dynamics, by and large, make use of things like Navier-Stokes, which are partial differential equations. So this is really what it's for. It can handle a lot of different kinds of meshes and structures and file structures, data structures that correspond to these. And all of the examples I am going to show you involve, I say all the examples, both of the examples, but 3 examples I'm going to show you are mesh-based in that sense. However, what these slides don't say is it also supports, to a lesser extent, particle-based simulations, meaning where the underlying physics are happening, not by solving systems of differential equations, say, across edges, but by integrating over some coverage region and representing that region using some sample particle, right? So think swarms or these sorts of things. Or don't think anything, just wait an hour and Adni will tell you exactly what she does, which involves particles. So that's the basic idea. And then attached to each of those vertices could be all sorts of variables, right? Variables associated with pressure and temperature and maybe velocity and all sorts of things that might be necessary for the underlying physics that you're simulating, right? Yeah, all right, we don't care. Okay, so basic user interface. Obviously, we have after my comment about Mac, the actual screen clip is Mac. All right, so it's got toolbars like everything else. The thing I really want to point out is this pipeline browser. This and the properties pane are the real heart and soul of the interface, right? So, and we'll talk more about how this pipeline works and allows us to put different layers, filters, and so forth that build up actually a hierarchy of the way that we filter and visualize things. And then, of course, we have a view pane, which we can see things in. Yeah, and we can control it like you can many WYSIWYG apps. I'm not going to get into that. I can build things in ParaView if I want. So for instance, I could go up to source, geometric shape, and I guess the example they're giving is a cylinder. So notice I selected the cylinder. I see the cylinder here in the pipeline, but I don't see anything on the right. So ParaView, no, you don't see anything at all. I'm not sure why it's not switching over. Now you see it. All right. So what I did was I said, can I make this a little bigger? I guess not. All right. So, I did sources, geometric objects, and I picked a cylinder, and this appears on the left-hand side in that pipeline. But of course, I can't see anything yet. This little thing which you can't see is an eye, and it's closed, so we're not visualizing it here. We're going to make heavy use of the apply button. The idea being that I'm going to mess around with parameters and so forth, and then apply and see what I want to see. In this case, I don't have any parameters I want to mess around with right this second, so I'm just going to apply it, and we see, I guess that's a cylinder. But the reason it's like this is because the resolution here says there's only 6 sides. I can increase that resolution and apply, and now I have something a little bit more like what I might imagine. Obviously, the higher the resolution, the more and more vertices I'm going to have in this mesh, and you can see it. You know, I can build I can look at the wireframe, or the wireframe with the surface. There's lots of different visualizations I can look at. I'll look at some of the others later. Put this back to surface. Right. Okay, so far so good. Make sure I'm following along so I don't get lost. All right, we did that, okay. Right now, this is just an object I constructed. It doesn't have any particular properties, so it's just plotting this with a simple solid color. It has a default color. I could go down here, so this object has all of these properties. I can look through, you know, which ones I find interesting or what have you. And if I wanted to, I could edit the color and pick a nice, you know, red. I could change the opacity of the object, etc. Move it around, zoom in, pan, you can do all that kind of stuff. Of course, not sure how much I care about that. If you hold down the X button when you're rotating, it will pin one axis. You can do that with Y as well, and you can do it with Z as well. I can also, if I get lost, and I don't know how you are, Adi, but I very frequently get lost when I'm moving things around the mouse. I can just go, you know what, orient it this way or this way, you know, positive X or positive Z or whatever. I can rotate by 90. I can. So I actually make pretty heavy use of these things, and I can sort of frame it back in the field of view if I get out of alignment or zoom. So all that's, nobody cares. If you get tired of having to hit apply all the time, there is an auto apply button. This one, yes. So if I were to make changes, like let's say changes in the resolution, it applies every time automatically. I strongly suggest for large things that you don't do that because the interface will drag, right? Because it will be possibly making recomputations across thousands or millions of elements depending on what's in your simulation. But it's tempting when you have a simple one to do that because I know for me when I'm playing with it, I'm very frequently looking at it going, why isn't it doing it? Why isn't it doing it? Oh, I didn't hit apply. But yeah, you got to do that. All right. Don't care about that, so I'm going to skip that. I did that already. All right, so going back to our oh yeah, so one cool thing about it is you can, each of those little data entry or sections in the properties pane, I can go to this toolbar and I can save out those properties. I could copy them, I can paste them from something else, which is kind of cool. And it understands the structure of them and can handle that, which is neat. Yes. All right. Yeah, we don't care. Get all that. Oh yeah. So the properties pane gets a little complicated sometimes, not for a cylinder, but for other things, as we'll see. So sometimes, you know, we're scrolling around trying to find the thing we're looking for. I can always search. So now I see what I need to see, which is very helpful. So far, nothing I've said is that interesting. It's just a 3D modeling tool. There are better 3D modeling tools than this. And in fact, a lot of people who do these sorts of, so you can do specular lighting and all that kind of stuff, which I'm not going to bother with. Did the auto apply. So a common workflow for these types of systems are you might use some proper 3D modeling tool to produce some sort of mesh. Sometimes the tools that you're going to be solving with have a built-in tool for that. Sometimes that tool is not so good, so you might use Maya or something like that to build a 3D mesh. Then you import that mesh into whatever solver that you're going to run, and you run that solver typically on some sort of high-end computational resource, which produces some result, and then you pull that into some visualization tool and you run it, right? Increasingly, people are trying to get these updates as the runs are going, because you can possibly imagine if I have this massive, let's say, combustion simulation, and it takes 2 weeks to run, and I realize after 4 days that it's not right, I'd like to stop it. So it would be really frustrating if I had to wait till the whole thing was done and then run it and realize, oh man, it wasn't right. So, and there are ways to do this with ParaView. It becomes increasingly harder, but that's the. So these are supported data types right natively right out of the box. You guys may not know a lot of these, but ANSYS is a computational fluid dynamics tool that's very common. OpenFOAM is an open source tool. I'm going to show you a couple of examples from OpenFOAM today. It reads all the visit files and Dyna. It can read most of the CAD type software, etc. So there's Gaussian if you molecular dynamics. It can read VAST, which also does computational molecular dynamics. So it can do a lot of those things, which is very cool. All right. So let's get something real here. We don't care about. So I have the 5.7 beta version, which has this nice little bug that if I hit this reset button, which is a very cool button to hit if you want to just go back to scratch, it actually crashes. So I'm not going to hit the reset button. Maybe if I had stuck with the proper 5.6 version. What version are you running? 5.6, yeah. Anyway, all right. So I load this. Of course, it's not visible yet, so I apply. Doesn't look so interesting. Looks like just a cylinder. I'm going to load all the variables that are associated with this. There's all sorts of variables associated with different compounds that exist, velocity, temperature, pressure, etc. Now, one thing I can do now that I have an actual object with variables that are attached to the vertices in the mesh is that I can say how I want to color it. So, for instance, I could color by pressure. I can color by temperature or velocity or anything else, right? I think if PowerPoint's in full screen mode, it won't let me switch for some reason. All right. So I loaded this file. I selected all. Why don't we start over? Yeah. So file. I'm going to load all the variables. Apply. So again, it just looks like a cylinder. But now I can select how what I want to visualize. Let's say I visualize pressure. Right. Now this example, I believe this example is is a ballistic example. So there's actually an object in there that's heating up. That's why this, and forming a lot of pressure. That's why this is red here. So let's get at that. So one of the things we can do with this pipeline is that we can add filters. I'm going to add this contour filter to it. I'm going to filter on, let's see, what do they suggest? I think temperature. So I can follow along at home. Yeah, temperature, that's right. Temperature, and I'm going to set my filter to 400 degrees Kelvin. Again, it's not applied yet. If I apply it, this is the region of that structure that obeys that filter. So I filtered out everything that was below that. Right? Now you might say, well, yeah, but I'd like to have seen the original structure too. So I can go back up to my original thing and I can say, I want to extract the structure from it and make that a filter as well. So I can visualize the structure on top of this. I can get to filters in lots of different ways. There's lots of filters here. Some of them I have a quick access to on the button. But anytime you get lost, you can do, in the Mac case, Alt. I don't know what it is on Windows. What is it on Windows? Alt space. To do a search for a filter?
Oh, I don't know.
I don't know. Anyway, so I just looked for extract surface. There I have that. Now if I apply this, now the problem is that I've covered over what I just did, right? So now what I'm going to do is I'm going to go back up to, I'm going to stay on the extract surface, and I want to cutaway. So I'm going to apply this clipping piece. Let's recenter this. I'm going to turn off the, I can move this pane around if I like and orient it how I want. I'll just stick with it like it is. I'll turn the pane off and then I apply and oops, let's do it this way. There we go. Now I can see inside that structure. Right? So I can see where it's gotten particularly hot. Right? The thing about this that's worth discussing is the pipeline. The pipeline is what makes ParaView particularly powerful. So there's lots of different filters. We're going to use some, but not all of them. I did all that. So so the way this looks like, what I just built, I loaded this original file. I built the contour filter from this, and that's how I got that, the hot region of that cylinder. And then I extracted the surface out from the original one and I clipped that surface, not the contour, but the surface, right? And you can build this tree however you like, right? You can add all sorts of features and whatever you like. When we come back to the end of the lecture, I'll come back to why, in addition to giving you the power of the analysis, it gives you help in terms of the parallelism in HPC world. Now, one cool thing that you can do also, oops, it's not going to work. Get out of the full screen mode. Right. Let's delete. All right. So I can open up these multiple views. I can also do this. I can say, you know what? Link these two views. And now, when I move one around, they move around together. And so I can have one showing me temperature, one showing me pressure. I could have one with streamlines and one without. And you can do as many of those in whatever orientation as you like, which is very cool. If you're trying to figure out what's happening with your simulation. Did all that. Yeah. So if you're used to differential equations, then you're used to, let's delete this. You're used to the idea of streamlines, so we're going to pick a direction vector through the surface. We can adjust this if we like, and I want the stream. Oops, sorry, the stream trace through that. Now that's pretty ugly. I think we can all agree. So we're going to change them to tubes. We're going to add that filter. Apply. Now I have these tubes, maybe decrease the radius a bit. You can see where the pressure zones are, etc. If I wanted to, I could add a glyph, let's say cones. On the velocity, so the size of the cone is going to correspond with the velocity. This scale factor is going to have to come down somehow. So now, oops, still too high. Yeah, it's a little better. So now, maybe make the tubes a little smaller. And maybe a little transparent. A little easier to see, maybe a little easier. So the color here is telling me about, we chose temperature, is that right? Pressure, that's right, pressure. But the size of these cones corresponds with the velocity now. So the larger the cone is, the larger the velocity. So there's this vortex going on, and we can see where the pressure is lighter and the velocity is high, etc. So this the direction. So you can use this to do all sorts of different kinds of scientific analysis. And of course, if you're at the end of the day, you're sitting there thinking, well, what I really need, let's get rid of all this, is data. You can still get data off of this. Let's do my Cutaway. So I could do plot data over time, right? Just overline. That's it. There we go. So this line, which is in 3 dimensions, there's different keystrokes to start and stop, or you can try to drag it and move things around, etc. I'm going to deliberately make it a little weird so we can see. I can move this around, and what it's going to do is it's going to sample along this line whatever thing we wanted to measure. In this case, we are measuring I guess we must be measuring the pressure from the original clip. And then we'll get, oh, actually we're measuring all of them. We can turn off what we want. That's right. So I can say, yeah, I don't care about these. Just give me the pressure and the temperature and whatnot. And I can reorient those panes how I like. I could go back, and find this line and move the line around so I get a different sample, etc. So I can see what things are through some cross section, etc. So that's all static. And There's lots of other things we can do. I can get a histogram of, let's close this. Delete this. Delete the clip. I think from the histogram it's, yeah, we go to the display. Turn off the variables except for pressure and temperature. Boom, boom. And then it's, oh, that's different. Sorry. Yeah, filters, data. Analysis. I can get a histogram of whatever properties I want, and I think I turned off too many properties. Oh yeah, you got to set the input range. That's right. Here we go. Let's do temperature. Or not. Tell you what, why don't we start over? There we go. So I can get a histogram of the pressure values in the system if I want, or whatever. And I can get lots of these. The panels. I can save out the files if I want. I can save out a given pipeline, so I can just load it back in if I want. There's all sorts of different ways of visualizing these, including I showed you some, but another one that can be good in some cases is this volumetric one. It's computationally pretty intensive. So, so ParaView likes to ask you, are you sure you want to do this? In this case, it's a pretty small object, so it's not that big a deal. And we get this, I'll show you an example later where I use this, I think, reasonably effectively. Don't care about that, so we're going to ignore that. I'm going to go back to the slides. Multiview. Don't care. All right, here we go. All right. So I've talked about this before. We like to use these rainbow colors for some reason. I don't know why. A lot of our tools default to these types of color maps for invariant variables. They're not good for most things, right? They're not good for a variety of reasons, one of which is colors don't really have an implicit order. And while you might say, well, there's Roy G. Biv, how many of us think numerically, then red is lower than blue, right? Is that very cognitively obvious to people? I don't think so. But also the saturation ranges of those colors are quite different, so they stand out differently. Like the red stands out very differently than this sort of teal color, right? So it has a different kind of effect in that sense. So it's better for numeric variables typically to choose one hue and change the saturation level or something along those lines, et cetera. Or to pick it in such a way that you're pinging between two specific colors. You're ranging between two specific colors, like say this one, right? And it shows you some different examples. Which you can do. You can have full control over the palette. So this is giving you that example. There's an implicit ordering here, right? I think cognitively we can very easily see that this is somehow related to this in a way that's less related to this, right? But I'm not sure that we have the same sort of relationship between, say, these three, unless you were to say, oh, well, red is at one end of the spectrum and blue is at the other end, so it must be like this, right? But I don't think that's sort of intuitively obvious. You have to appeal to your knowledge of the way you did, right? So just as an aside, I know we've talked a little bit about that before. So there, he's giving you an example in this space where we're going between two colors, red and blue, as opposed to this rainbow color, which is it's harder to understand what it means. And it talks about the perceptual unevenness. We can skip through all that. Okay, so what I showed you was a static image. That's the example that they give for that. That's not really where ParaView is really cool. ParaView is really cool when you have something more dynamic. There's a bit of a deliberate problem with this simulation output that they want to go into in their slides to explain how to fix. I don't really want to get into the issue, but it has to do with establishing the correct ranges and colors so that they don't bleed out when the values get very large, but beside the point of our discussion. So we have this, this ominous, there we go, ominous unit hanging above this half cylinder, and I can watch the results of the simulation of this heavy weight crushing the cylinder if I want. But aside from just the cool, hey, I like to see things get crushed, and hey, who doesn't? I could say, well, show me what the displacement looked like when I did that, which I guess is not too interesting, or the velocity of the nodes, so you can see the leading vertex in the mesh as it pushes the thing. So you can look at these different variables, and we can do all the things we did before. We can put cutaways and streamlines and all this stuff and watch them over time, right? So, and we can drop lines through it and watch and plot the values of something over time, which is very nice. Yeah. I did all that. Don't care. So there's some, you can drop annotations, you can do all that kind of stuff in there. We can also do queries, so this is kind of cool. Is it, trying to remember the, find data, that's right, edit. So I can say, let's take a look at this EQPS. I want to look at it when it's greater than or equal to some value, let's say 1.5. I'll run the query selection. I don't know, you can't really see it here, but yeah, there we go. So now we can see the region. So this is where that variable was like this. And you can select on these things, you can change the color of them, you can do all of this kind of stuff. You have one view that has a region in it, one view that doesn't. You can run those sorts of queries and visualize over and over and over again, or some region of it, etc., if that's what you need to do. So it's got all those features, if you will. You can brush things and let it watch over time. We talked a lot about brushing and dynamic. We can make a video, so even if it takes you 4 hours to render the visualization, I'll show you one later that's pretty slow. I can make a video and then later play the video at whatever speed you want to, right? All right, so that you can do all that. We can not only play the video, but you can actually, I guess if you want to do this sort of stuff, we can have the camera orbiting as it goes, right? So the thing is crushing and the camera is moving, all that kind of stuff. and we can render that video. That's neat. All right, so this is maybe a little bit more what people are here might be interested in. Not only can I do this, but this PV Python shell allows me to run Python scripts that put all this stuff together. So I can run my simulation and I can produce the visualization in ParaView without having to go through the effort of loading it up and doing all these things. And in fact, actually, I can trace. I can run the tool, go through all of my steps, trace it, and then output that macro, and then edit the macro. Or I could write it manually, right? I could create the parameter here. We've created a sphere, and we're showing it, and yada, yada, yada. We can break it up, and make it go out and shrink, and we can do all that kind of stuff, and we can do it in code in Python, which is pretty cool. Read our files if we like. We can query things in code if we like. All the stuff that we can do in the command, in the interface, we can do that. We can produce plots. You can actually write ParaView to do the plots that we've been doing all semester in R, or many of them. Right? I could write Python code that pulls in a CSV file and plots it as a line plot, etc. I have no idea why you'd like to do that. Maybe you're just a glutton for punishment, maybe you hate life, but you could if you wanted to. But it is relevant if you're doing this large-scale simulation and maybe you want to also produce plots related to that simulation without having to go through another tool. I tend to think if you're going to be producing data visualization plots, you're probably going to export the values and pull it into a tool that does that better. But I'm biased. I believe that's how Adni does it, but she might be biased because that's how I do it. But the data visualization tools in ParaView are suboptimal, but it does save you from having to export some data file related to whatever, if you're doing a cutaway or something like that. So they go through some example. Here's an example of a shock wave. Here's an example of some climate modeling. 500 million cells in the vertex. Here's a fire. It's just a still shot of it. There's all sorts of different, so forth and so on. Okay, so this idea of a pipeline is really useful, not just because we can build our visualization that way, and you can think about it that way, which is really logical. I'm going to have this is going to be about temperature, but only the piece that's 400 Kelvin and above, and then this is the cylinder and pressure, and I'm going to cut it away, so I can build, sort of hierarchically that way. But also because these different components of the pipeline, in many cases, can be split up. And if you think that each of these, like computing streamlines, is not a trivial task necessarily for a large-scale thing, so you can shuffle it off to its own computational server and let somebody else, some other server, handle some other part of the rendering. So we can break up our data visualization. We can even handle cutaways and clipping and things like that in a distributed fashion, which is quite nice. There are some artifacts here, though. For instance, you can't. Oh, here. Let me. So here's a parallel rendering task, etc. If I'm running many servers out there to do these various things, and I'm running a client, I can't really do occlusion until I get to the client, right? So in other words, I'm at the client, and I've got this 3D thing, and I rotate something. Now something behind it is occluded, right? But the individual server doesn't know what the viewpoint is, right? So it can't know what to occlude. It can only know about clipping when it comes to the clipping filter or some sort of rough clipping that happens because of the frame, etc. So as a result, all of the objects still have to come back to the client, right? So, so that's a downside. So a lot of people don't do it that way. For instance, TAC, the Texas Advanced Computing Center, the way they have their ParaView setup arranged is that, yes, they'll do it client server, but you actually log in using a VNC session into their visualization cluster, and all of the client server stuff happens inside the cluster, and then you're interacting with the client over VNC. So the client's not even running on your computer, it's running in Texas, right? And that's because they want to make sure all of that computation, including the occlusion, happens on the cluster and not, and that you're not sending millions of vertices across the, or data points across the height. That's relevant to a lot of things. So forgetting scientific visualization, another student of mine and I had a paper this year where we were producing these graphs of like cities, right? And visualizations on top of those graphs. Unfortunately, I don't know if you've ever looked at the road network for a large city. There's a lot of roads. So I use LaTeX. So I have to build the documents. If you're using Word, it would be the same thing, the documents to load. And I told you at the beginning of the semester, always produce your data visualizations as a vector graphic if you can. But what if you have millions of things to render? Then when you're producing your data visualization, you go, I don't know if you've ever pulled up a PDF and had this problem of the actual data visualization going to building as you're going, right? Because there's just a lot of things. And often, a lot of them are occluded, right? So from a scientific data visualization, this happens quite a lot, because you often have these very, very large things, and I don't want to send 10 million units to the client, right? If 9,560,000 of them are going to be occluded, right? So you can handle that in the way that I just described, but also another way of handling it is instead of rendering this way with this sort of standard 3D modeling rendering framework, you could do ray tracing or path tracing. So ray tracing, the way ray tracing works is like your eye but in reverse. How many people have ever heard of ray tracing? Right. So imagine instead of light going from the light and bouncing off of this and then hitting my eye, I'm going to shoot a ray out of my eye. It's going to hit and go back, and then I'm going to note the color, right? And if it refracts, I calculate that. If it reflects, I calculate that, etc. And that's your 10-second version of something that's literally 20 years of computer graphics in the making. So I'm not going to go into great detail, but the great thing about ray tracing is if you ray trace the image, then occlusion is handled naturally, right? If it's occluded, you'll never hit it, right? So I don't have to worry about that. So there's that. It also, ray tracing, a good ray tracing engine looks very nice. It handles all the lighting and so forth correctly if it's well written. And so your final product, what you see, can look very nice. Of course, the downside is you're not going to grab your cylinder and rotate it, right? Because every view is going to have to be retraced, right? So ParaView can handle ray tracing. VMD can handle ray tracing. We'll actually do that when we're in there. But that's what you do at the end, right? When you're done, you ray trace, and then you have this really nice image, right? And it looks pretty, etc. But now the image is not a vectored graphic, right? It's a rastered graphic, and it's not gonna. You gotta produce it to the scale that you want it. It's not gonna scale well, right? Okay, so so this was the idea that you can break up rendering and yada yada yada. So there's multiple ways that you can run something like ParaView. The way that we're running right now is this way. There's a client, there's a render server, and there's a data server that's handling the data. It's all just run in one package. I can run it like this, so that the data server and the render server are together, and I have many copies of them on, say, Newton are clustered downstairs. And then I'm running the client either remotely or on another compute node, etc. And then still a third way to do it is I can handle all the data manipulation in a distributed way too. to reduce those things. All three modes are supported in ParaView, which is nice. Visit does something similar. Yeah. So if you've never heard of MPI before, it's just a standard to define message passing for large-scale distributed computation. It's the de facto standard for large-scale distributed. There are many implementations of MPI. So MPI is not a library, it's a standard. There's OpenMPI, there's Vortex, there's Intel, there's such. And Microsoft, don't use Microsoft. All right, so yeah, we're not gonna do any of that. Pass that. All right. So I talked about all of that. Let's show a real example. So I have delete this. This one's good. This one's fun. All right. So I took some of the examples that came with OpenFOAM, which is a differential equation computational fluid dynamics software that's available for free, and I ran some of them on our cluster, and I have the results here. So I'm going to load this one. This one is a 2D simulation, so it's going to look a little weird in ParaView because ParaView really wants to be 3D. I have to tell it it's OpenFOAM right here. Okay. I think I wrote down which, yeah, okay, I figured it out. Not that one. This one. And oops, wrong view. There we go. So that's pretty cool, huh? It's a little weird though, because if I rotate it, it's like, what? Because it's really a 2D simulation, but ParaView doesn't really do 2D, you just map it, project it onto some surface. So that's one. Here's another one. Oops. Look at the water. There we go. And I'm going to do this one. This. I'm going to add surface back, except I'm going to render that as, oops, to apply it. I'm going to render that as, no, featured edges. There we go. Control, turn that back on. And so yeah, this is a little slow. My laptop is not the greatest laptop in the world. I don't have any kind of modern graphics processor and so forth. But even if this is slow, I could be recording the movie. Right? So this is water sloshing around. A little tank that's moving around. Now you might say, so what? I've seen this a bazillion times before. But this is not This is not a computer graphics technique to look like water. This is a simulation of water slashing around with all the properties associated with it, right? So we ran this simulation at whatever resolution we want to get as the most realistic result we can get. This particular one may not be greatest, but so it's not just a matter of getting something that looks like water splashing. It's a matter of getting something that is physically accurate as possible, not just according to its visualization, but also other properties like temperature and blah, blah, blah. So there you go. That will be relevant later to what Ani's doing. All right, so that's kind of cool, I think. It doesn't like, all right, so we're gonna close ParaView. So that's ParaView. There's a lot more to it. It can do a ton of stuff. I know most of you don't do that kind of workflow. However, it gives you a good idea of what scientific visualization is about. Right? Scientific visualization is really about understanding the physical world in that sense. Yeah. So that's ParaView. ParaView is a general tool. Let's talk now about VMD. So VMD is a very specific tool. It's about visualizing molecular dynamics. I'm not going to show you anything dynamic today, but I will show you some molecules. It reads some specialized file types. In particular, it reads, thank you, this PDB, which is a protein data blah, blah, blah file, which is, contains a lot of information about molecules themselves. Okay, so all right, so that doesn't seem terribly interesting, but the cool thing is I can play around with all the representations for this structure, right? So right now it's just sticks colored by whatever, lines, if you will, that are colored in this case by the name of the underlying atom. I can change all of that, but what I'm going to do is first change the drawing methods to the van der Waal, the thing that we're I think used to seeing frequently, and I can change the size and make the resolution a little better, etc. I can even, I like brushed metal. That seems awfully nice, right? So I've got my molecule. I can, if I want, have more than one representation. So if you like this, if you like the sticks, they can still be there, right? And I could maybe color this by, is it one related to the bond? Not so much. Charge is probably not going to be interesting. Yeah, I don't think so. There are also all sorts of other really cool representations. So a lot of these molecules have very specific high-level properties that chemists and physicists care about, like whether they form these helixes, the direction of what are called residues in the molecule, which are places where charges leave off, and things like that. So you can put those sorts of visualizations in. Let's make this thicker. Etc. You can also do things like, you know what? Let's first of all, I'm going to turn off these, so I just have the van der Waal, got a little clipping there going on. And now, what I want are just oxygen, or so what was the cool one they had? They had a really neat one. I like the filter. So it takes a fairly robust, yeah, that's it. So if you want to say, don't show me anything, any of the molecules that are involved in a helix, and don't show me anything that's involved in what's called a beta sheet, which I'm not going to get into. That's what's left when you're done, right? And you could say, you know, I want all those other pieces still there. One thing you could do, for example, is let's go back to this one and say all. Doing all. Right, boom. Put them back. All right, good. Now I could say add new van der Waal. In this case, I'm just going to select I don't know, nitrogen. Apply. I'm going to make these spheres bigger. Oops, too big. Transparent. So I highlighted the nitrogen, right? So you can do all of that kind of stuff. There are different kinds of 3D rendering. So there's one that preserves parallel lines, but it sacrifices depth perception, and there's one that's where depth perception is better for us on a 2D projection, but instead it's harder to see when things are parallel, right? And you can render in either of those mechanisms, etc. And then let's see. Yeah, so we can also extensions data, oh, analysis, that's right. Oops. Darn it. Trying to remember which search it was. Sequence viewer, that was it, yeah. So this is a protein. Proteins involve sequences of amino acids, if you remember your biology. So one of these is a sequence viewer, but I'm not seeing it. Third from the bottom. Yep. Thank you. So now I can jump around and see the different amino acids in the molecule, which is pretty cool, right? Select the ones I want. This is also completely scriptable. We have people on our cluster who run a molecular dynamics modeling software called NAMD. Lost my coffee mug. No! Oh, here we go. I have to remember what's important. And then part of his workflow, I mean, he sends his batch job out. It says, set up the simulation, run the simulation. When it's done, he runs a little set of scripts that scripts VMD that produces the visualization, highlights what he wants, and then he ray traces it. I'm going to show you in the other room the ray trace. I'm not going to try to ray trace on my little laptop. And there's a ton of stuff it can do. It can also handle molecular dynamics. I don't know how many of you read Nature, but from time to time you'll see a little molecule on Nature. Dollars to donuts, it was done in VMD. So all those sort of covering areas that you see over them that show you potential wells of energy, all that's possible in VMD. I don't want to get into specifics because I think this is even less along the lines of what you guys are interested in, but I wanted to show you the difference between an example that's a quite general tool for lots of scientific visualization and an example of one that's particular to a particular science. A lot of the molecular dynamic stuff can be done in ParaView, but it can be done better in VMD, right? So, ParaView is not going to understand what a protein sequence is, right? You're just going to manually say that's where it is, right? Okay, so that's all I'm going to show you myself. What I'm going to do now is turn it over to Adni, and she can show you how she's using ParaView for her research. When she's done, we'll go as a group to the next room over, and I'll show you VMD on the big, huge viz wall, and I'll show you what the difference between a ray traced image and a rendered image is. And then when we're done, we'll go to 220, and we'll see on these stuff again, but in 3D. Okay.
I might need some help with connecting here. So do I just take the HDMI from you and put it in.
Yes.
Thank you.
I'm gonna stop the video though, because sorry people at home, should have come. It's super fun. You can't see it. Everyone in here is smiling.